let's start. Let me start with a kind of general question. Up to now, you've seen all the courses. So how are you surviving? Does it work well? Kind of. What's your general impression or first impression? Let's say. Any complaints? Any questions about the?
About how much problems we have. I don't feel like I can do all of them. Are we expected to do all of them?
Oh, but that's you mean if you take all the courses in total? Oh, I think that's fine. I think it's better if you have more problems than you can handle than if you just don't have enough and you don't know, like kind of you say, oh, it's all boring or it's all trivial. So yeah, you have too many problems. Very well, just make your choices, work out your strategies, right? Some of the courses will be more interesting for some of you. Some of the courses are whatever, maybe less interesting, or some of them are easy, some of them are difficult. But that's probably kind of, life. Life is like that. Some things. So that's okay. You shouldn't worry about it. Any other things? All right. So last time we saw a glimpse of symplectic linear algebra, and today we want to see the basics of symplectic geometry. Many of you are probably familiar with this stuff, but still, let's go through it and let's set up the basic concepts in place. So today we'll have some foundations of symplectic geometry. So let's say M is a manifold and omega is a two-form on M. So that's the notation that I'm going to use for differential forms. At the point M, it's a skew-symmetric bilinear form on the tangent space, or an element of which two of T star MM. And so we were discussing this situation last time. So we have a vector space, so the tangent space at the point M, and the skew-symmetric bilinear form. And so this vector space is symplectic. Means that the kernel of this form is 0. So in fact, here there is a kind of a little bit of confusion with terminology. So we say that the symplectic the vector space is symplectic, or we also say that omega M is non-degenerate, referring to this condition. So the kernel is 0, so the corresponding form is non-degenerate. Now, so the confusing part is as follows. So we say that this pair, a manifold, together with a two-form, is symplectic if two conditions are verified. And the first condition is that omega M is non-degenerate for 2 points of our manifold. You see, so it's a bit strange. Before, this condition was actually called symplectic, but now this condition is called non-degenerate. It's only part of the symplectic condition. But I hope it doesn't lead to too much confusion. And of course, the second very important condition, d omega is 0, so it's a closed two-form. So there are two conditions in this definition. So, well, this definition, again, it's not completely obvious to start with, but this is a very, very successful definition, a hugely successful definition, which gave rise to a big field of mathematics. it's not clear why 2 form, why not 3 form or 5 form or 1 form, why closed, or I mean, right? So there is it's not completely clear to start with that it's going to be a good operation, but it is a good operation. So we'll see parts of it, maybe not major parts of it, but some parts of it we'll see. So let me give some simplest remarks about this definition. First of all, of course, M omega symplectic implies that the dimension of the tangent spaces, so tangent spaces are symplectic vector spaces, so the dimension of tangent vector spaces is even, and this is the same as to say that the dimension of M is even, so symplectic manifolds are even dimensional. So maybe the next remark is as follows. Let's denote by capital N the dimension of our symplectic manifold divided by 2, and let's consider the top degree form omega to the power n divided by n factorial. So, so this is again called the Liouville volume form, and in fact we know that for any point M in M, so this is a symplectic vector space. What we discussed last time, the top degree of the corresponding 2 form is non-zero, and so this means that this is a nowhere vanishing top degree form, or in other words, a volume form. So this is not 0 because we know from symplectic linear algebra it doesn't vanish at all the points of M. In fact, if M is compact, no, wait, one more remark. So we have this nowhere vanishing volume form, and in particular this implies that M is orientable, and in fact it has a canonical orientation, so the orientation given by this volume form. This canonical orientation defined by L. Now, if M is compact, we can integrate this Liouville form over the manifold, and well, this is called the symplectic volume of M, so it's associated to M and omega. From the definition, it's clear that it's always positive. And so this is an important data, an important number you can associate to a compact symplectic manifold. So later on, we'll have quite lengthy discussions of those symplectic volumes, or how to compute them in some particular situations. But this is the first time that we see. Now, maybe one more remark. From our discussions of last time, we know that there exists a unique element of wedge 2 TMM. So for any M, so there is a unique element in this second exterior power such that phi m sharp is equal to omega flat m inverse, right? It's easy to convince oneself that so this assignment at each point defines a smooth bivector. So bivector pi, meaning a section of the second power or second exterior power of the tangent bundle. Right? So these are just values of this bivector. It's smooth essentially because we have a smooth invertible element. We can, let's say locally, we can think of it as a kind of matrix, right? So this is a smooth invertible matrix. Its inverse is also smooth, and it defines this guy pi. Right. Okay, maybe these are the first remarks. Let me give one more definition. So we kind of defined a category, right? So we have a category of symplectic manifolds. But at the moment, we only defined objects. The reasonable question is, what are the morphisms? And in fact, it's a more complicated issue that one may think about. I'll now give you one definition of morphisms, which are called symplectic morphisms. But in some way, this definition has deficiencies. But we'll have to live with it. Maybe later on, I'll tell you about the other versions or the other ideas that one can use. So, right. So definition. Suppose we have a map F between two symplectic manifolds, M1 and M2, with symplectic forms omega 1 and omega 2. So is a symplectic morphism. If the map itself is a diffeomorphism, and the pullback of omega 2 on the F to M1 coincides with omega 1. So you see this is a very, very restrictive definition. So sometimes people want some more relaxed definitions to have more freedom, because with this, of course, there are symplectic morphisms, but there are not that many symplectic morphisms in this category. Maybe notation. So SP M omega. So this will be diffeomorphisms of M such that the pullback of omega coincides with omega. Note that actually this is sitting inside diff plus of M, where plus is orientation preserving diffeomorphisms, right? Because we know that the orientation is canonical is defined by the symplectic form, so therefore so orientation preserving. So there is an infinitesimal version of this construction. So I don't know whether you're using this kind of funny symbol for vector fields. right? So symplectic vector fields on M. So these are vector fields on M which preserve the symplectic form. So the Lie derivative of omega should be 0. We'll discuss the relation between these two things in a second, but first I think I forgot to say something here. Maybe let me add some small comment to this part of the blackboard. So let's return for a second to this discussion of the symplectic volume. So if M is a compact symplectic manifold, we said the symplectic volume is well defined and always positive. In particular, this means that the cohomology class of the Liouville form is non-vanishing, right? Because if it were vanishing, then this integral would have been equal to 0, and this is not the case. But if this is true, this means that the cohomology class of the symplectic form itself has to be non-vanishing, because L is a power of the symplectic form. If this were vanishing, then the class of L would have been vanishing. But this implies that the cohomology group where this class lives, H2 of M with real coefficients, has to be non-vanishing, right? And this is an important topological consideration. So we see, and this is one of the simplest ones, we'll see kind of further topological restrictions. For instance, what you can say for the simplest situations, if you take an n-dimensional sphere as n, then we see that it is not symplectic unless n is equal to 2, because for n equal to 2 we do have H2, but for other n's we don't have H2, and therefore we cannot find a symplectic structure on n-dimensional spheres. So let me return to the relation between symplectic vector fields and symplectomorphisms. So this is just perhaps to set up notations. So suppose that we have a smooth family of diffeomorphisms of M, and let's define the two forms alpha t as pullbacks of omega under Ft. And well, for simplicity, we can think that F0 is just the identity of M. So this means alpha 0 is equal to omega. So t is a real parameter. So then let me recall the formula for the derivative of alpha t. So that's the derivative of Ft star omega. So let me write the formula and then introduce the notation. So this will be Ft star. Let's see. Hopefully I'm not mistaken. You'll tell me whether I do it correctly. So where Vt of M is something like this. D over ds roughly. Doesn't sound correct? So one can define, having this family of diffeomorphisms, one can define also a family of vector fields. So this vector fields, this is roughly the derivative of our diffeomorphism in the diffeomorphism group. And then there will be this formula relating the derivative of the form obtained by the pullbacks with phi star t and the Lie derivatives. Does it sound roughly correct? Okay, if later on you have doubts, you tell me. Right. But here, what is important for us? So notice that it works in two directions. So assuming that L Vt omega is equal to 0, so if your family of vector fields consists of symplectic vector fields, this means that d over dt alpha t is equal to 0, right? So the right-hand side is equal to 0, then the left-hand side is equal to 0. And then this means that alpha t is equal to alpha 0 and is equal to omega. And Ft is a symplectomorphism. Of course, the other way around, if Ft belonged to the group of symplectomorphisms, so then d over dt of alpha t has to be 0 because alpha actually doesn't change. It's always equal to omega. And then this means that the pullbacks of LVT of omega vanish. But since Ft is a diffeomorphism, so if this is 0, LVT omega is also 0. And Vt is a symplectic vector field. So whenever you have a smooth family of symplectomorphisms, you can differentiate them and you can obtain a family of symplectic vector fields. If you differentiate at one point, you get a symplectic vector field. And if you have a family of symplectic vector fields and you are able to integrate them to a family of diffeomorphisms, right? Because this is not guaranteed. This depends then on the details of your manifold. Say, if your manifold is compact and your family of vector fields is, say, smooth, then of course you can always integrate and you obtain a family of symplectomorphisms. Okay. Now, let me make one more remark which leads to an important definition. And with this definition, when I started preparing the lectures, I think at least to me there is a big confusion with the signs, but so maybe we have to discuss what are your preferences there. So let me start with a remark. So suppose f is a smooth function on M. So then there is a unique vector field on M such that the following equations are satisfied. So I will write two equations, and one of them in two forms. So the first equation says that pi sharp of df is equal to vf. Now, maybe one comment here. Before all these things, right, so at least this pi sharp, we were defining it at every point. But I mean here, so pi sharp m, it was defined as a map from the cotangent space to the tangent space in a given point. Now let me just denote by pi sharp the corresponding bundle map, right? So these were maps between fibers of some vector bundles. Now let's just unify all of them into the notation pi sharp. So pi sharp of the Durand differential of f is equal to this vf, or so which is of course the same omega flat of vf is equal to df, or let me just, okay, this is just writing it in a different way. So that's the same equation, but sometimes people write it this way. So of course, it is obvious that such a vector field exists and is unique because it's simply defined by this equation, right? So you have this pi sharp map, you apply it to df, you obtain vf. Since this guy is invertible and its inverse is omega b, so then this equation is also satisfied, and this equation is just the same as the second form. Here I do have a kind of sign question. So I write it here with a plus sign, but I think one can probably imagine writing it with a minus sign. Apparently, as I learned, as I said, preparing the lectures, so the choice of a plus sign leads to some relatively strange formulas that we'll see in the second hour. But, okay, so I don't know. Do you have some ideas or preferences about those signs? All right, so let's stay with this choice. At least my sources, they suggest this choice, but, well, I don't know. We'll see. Okay. So the name for it, as you probably know, is a Hamiltonian vector field of f. So let me already here introduce a notation. So H Hamiltonian, M omega. So this will be vector fields on M such that there is a function, a smooth function on M, which produces such a vector field as a Hamiltonian vector field. So this turns out to be a very, very important concept. And now we'll see the simplest properties of those Hamiltonian vector fields. So let me formulate a relatively lengthy proposition. So the first point which contains several statements. So those Hamiltonian vector fields are contained in symplectic vector fields, and it is a Alekseev algebra. by the way, so this implicitly assumes that this gadget is a Lie algebra, right? So of course we know that vector fields form a Lie algebra. Now, kind of I assume without saying that symplectic vector fields form a Lie subalgebra of vector fields. And why is that? Is it obvious? Is it not obvious? Let's open a parenthesis and see, right? I mean, this part of the proposition. So, by the way, right? So, why is that? So suppose we have U and V. Which are symplectic. So this means L of U omega is 0. L of V omega is 0. And we want to know what's the value of L of UV omega. So why is it 0? Well, just tell me. Of course, it's very easy, but make me happy. Tell me why.
We have that formula. Like, that's equals to...
Right? So this, you mean...
Yeah, right.
You mean that's the commutator of the two Lie derivatives? And then now it's obvious that it's 0 because each of the Lie derivatives kills omega. Right. Okay. So it's a Lie subalgebra. So that's the first thing. Now, so there is a map from C infinity of m times C infinity of m to C infinity of m, called the Poisson bracket. Poisson bracket. And it's defined by the following formula. So it's LVFG or minus LVGF or omega VGVF. So in particular, of course, the statement is that all these expressions coincide. And the statement is that it's a Lie bracket. And finally, the map from C infinity of m to Hamiltonian vector fields, defined as F map to VF. Is a Lie homomorphism. Under the natural bracket of vector fields on Hamiltonian vector fields and under this funny Poisson bracket here. Okay, so let's try to prove it. All right, so first of all, we need to know that Hamiltonian vector fields are actually symplectic. So let's say we have F in C infinity of M. Vf is then a Hamiltonian vector field. And we want to compute L, the Lie derivative of omega with respect to Vf. Well, that's the Cartan's magic formula, which helps us. And you see, so that we're going to see relatively often. So there is a kind of conspiracy between all the terms. So here, so this is 0 because d omega is 0. Now for the first term, we have an equation for the contraction of omega with Vf. So this is equal to df. And now because the de Rham differential is a differential, it squares to 0, and the result is 0. Right, so that was really easy. So Hamiltonian vector fields, they are symplectic. Now, why do they form Alekseev algebra? So here, let me show you my proof. But I don't know. Maybe you can find a better proof. So so we take two functions, and well, you take corresponding Hamiltonian vector fields. You take their Lie bracket. And you need to contract omega with this Lie bracket. Right. So the question is what it is. Now, first of all, I use one of the Cartan's formulas. I represent this contraction with the Lie bracket as a commutator of a Lie derivative and a contraction. Now, this is L Vf iota Vg omega minus iota Vg L Vf omega. And this is 0, right? This is 0 because Vf is Hamiltonian, hence symplectic. And if it's symplectic, then it kills, the Lie derivative kills omega. So this, we don't need to worry. So this is 0. Now, what about the first one? Here, let's use again the Cartan's magic formula. So it will be this expression plus iota Vf d iota Vg omega. And this is 0 because, you know, we just computed something which is exactly like this, right? D of iota Vg omega. So here we computed d iota Vf omega, and it was 0, just some lines above. So this is actually 0. So this means that in the end of the day, we get d of something. And this something is equal to omega of Vg Vf. Right? You first make the first substitution, and then you make the second substitution. Right. In particular, if you only want to prove the first point, we actually don't care what this guy is here, right? We just care that it's d of something. Remember, Hamiltonian vector fields, these are vector fields which are produced by this construction, right? So you put You put a contraction with this vector field into omega, and the resulting function is, the resulting one form is exact. That's what we want. So that's this resulting one form on the right-hand side is exact. And this shows that Vf, Vg is Hamiltonian. Right. That's because of this D here. Well, now let's try to prove the rest of it. So the next claim that I want to prove is the following. Remember, so there were several expressions for the Poisson bracket. So let me first show that all these expressions are equal to each other. So we have this omega of Vg, Vf, and I said, so it was equal to iota Vf, iota Vg, omega, right? Now, well, but let's use the fact that this is a Hamiltonian vector field. So this is iota Vf dg. Well, now we are kind of turning in circles. Use again the Cartan's magic. So this is L Vf minus d iota Vf g. But this term acting on g is 0 just for dimensional reasons, right? You have a function which is a 0 form. You contract it with a vector field. But there is no place, nowhere to contract. So when you contract here, you just get 0 by definition. So it's, right? So it is equal to L Vfg. And recall, this guy is clearly skew-symmetric with respect to the exchange of f and g, right? Because omega is skew-symmetric. But then this means this is the same as minus LVGF. Because everything is Q. Okay. So what's remained to be seen? So we showed that Hamiltonian vector fields form a Alekseev algebra. We showed that different expressions for the Poisson bracket, they coincide. Now the question is why this Poisson bracket is a Lie bracket. So Lie bracket, you need to show two things, skew-symmetry and Jacobi identity. So skew-symmetry is obvious from this expression, right? So Poisson bracket is Lie. On skew symmetry, we can put a check because we already know it's skew. Now, what about Jacobi? So let me write a triple bracket. FGH. Now, what is it? It's L of Vf, L of Vg, H, right? And I've chosen this way to write it, right? That's one particular choice, how I can write the bracket. So I want Vg to act on H and Vf to act on the resulting function. Now, let me, so in the Jacobi identity, right? Let me add with a minus sign this guy. I think that's one of the terms of Jacobi. Skew symmetry I am already assuming. So this will be minus LVG LVF H. Okay. So let's add them up, right? As in primary school, we write two numbers, one under the other, and we add them up. So let's see what this exercise gives. So here we're getting a commutator, right? A commutator of VF and VG, which is acting on H. And now I claim that so VF VG is equal to V of the Poisson bracket FG. So why is it true? So this is true. Probably not very visible. This is true because this is equal to this. And this is just a definition, right? So you take this function. So this function is by definition the Poisson bracket of f and g. So this function is actually equal to the Poisson bracket of f and g. So so this is equal to the Poisson bracket of f and g h. And now you've got three terms. So 1 minus 2 is equal to 3. And I'll let you check that these are correct. So in the Jacobi identity, you're supposed to have three terms, right? That's what I remember from the primary school, and these are hopefully the right three terms. And yeah, we have 5 minutes over time. Let me just say one more phrase to finish the proof. So there was one more point that we haven't covered, and so we proved that the Poisson bracket is a Lie bracket, and now we should show that the map from functions to the corresponding Hamiltonian vector fields is a Lie homomorphism, right? So what does it mean? So the map C infinity of M to Hamiltonian vector fields is Lie. So what does it mean? It means VF VG equal to V FG, right? That's the meaning of this statement. But you know, we're kind of just lucky, right? Without noticing it, we already proved it, because that was the claim, and the claim was proved on the other blackboard. So it is actually correct, and that's why the map from functions to Hamiltonian vector fields is a Lie homomorphism, right? So just fortunately, that's the formula we need to prove, and that's the formula that we just proved 1 minute ago. Well, so we're just lucky and have a break. So what I want to do during this hour, we're going to look at the simplest examples of symplectic manifolds and of symplectic structures. So let me start with the very, very simple example that I guess all of you already seen, perhaps many times. So we take the real vector space R2n. Suggestively, we introduce a coordinate system with coordinates q1, qn, p1, pn, and we define a two-form. And here actually, I have a slight problem with my formula, but well, so all my life I was used to dpi with dqi. But it sounds like with the definitions that we already installed, we should probably have dqi, dpi. But well, of course, that's just a sign question. I don't know, what are you people used to? Well, should it be dp dq or dq dp? dq dp? All right, so then that's right, and it's written on the blackboard, which is a good news. Right. I always thought it should be dp dq, but well, it looks like the truth is dq dp. Or whatever the truth. The definition is dq dp. Well, it's easy to calculate the Liouville form. So the Liouville form will be just the product of these guys. So it's volume form. It defines for you some particular orientation of this R2n. And perhaps let's write a Hamiltonian vector field. So for f is smooth function, the Hamiltonian vector field, and now I should try to get the sign right. I think it's in particular, one can also write this vector field, write an equation for the flow and this equation will be like just reading from here. So will be qi dot df over dpi and pi dot minus df over dqi, and this should be the right canonical equations from mechanics, right? So this should match with what we are supposed to see in mechanics. So I don't know. So I take canonical in parentheses because, of course, these equations in some way depend on various choices. Here I've actually chosen the coordinate system q1, qn, p1, pn. But still, historically, the word is canonical, which is used in relation to these equations. And maybe one more thing. So the bracket, Poisson bracket of f and g. So this is L Vf applied to g, and this will be df dpi dg dqi minus df dpi. All right, so these are the very standard formulas for the canonical, or whatever, for the standard symplectic structure on R2n. So the second example. M is an orientable manifold of dimension 2, and omega is any volume form on M. Since by assumptions M is orientable, those volume forms exist. There are many of them. Well, an example might be a two-dimensional sphere. We already discussed that spheres of other dimensions, they cannot be symplectic, but a two-dimensional sphere can and must be symplectic because of this consideration. Now, let me just say why two manifolds. So that's because here the condition d omega equal to 0 is void, because there is kind of d omega is always 0, whatever volume form you take, right, for dimensional reasons. So there is no constraint imposed by the Durham differential on omega. So that's why it becomes so easy for two-dimensional, in the two-dimensional case. So the third example, it will be a small chapter in our story, and it is called cotangent bundles. So I'll now explain the construction of the canonical, of the standard symplectic form on cotangent bundles. But before doing that, we probably need a little bit of preliminaries. Again, perhaps you know it very well, or maybe not. So let's say Q will be a manifold, and our M will be the cotangent bundle of Q. I'll use pi for canonical projection. And well, here I don't know, like, does it disturb you that this is the same letter as we use for bivectors? Or in principle, we can replace it by p, but then I will be mixing it up all the time. So whatever. Let's say pi is a canonical projection from T star Q to Q. And let me make the following remark. So suppose that alpha is one form on M. Of course, being a one form on M, what are one forms on M? So these are sections of the cotangent bundle, right? But geometrically, what are sections of the cotangent bundle? So let me try to perhaps make a diagram and possibly a drawing, even though with drawings I don't, sorry, Q, yeah, right. So T star Q to Q, so we can imagine something of the sort. So this is our Q. And this is T star Q. And somewhere in the middle, right, this is a vector bundle. So in the middle sits in the zero section. Zero section. Now, what is this alpha? If you think of it geometrically, alpha is a map which goes from Q to T star Q. Right? So for instance, if you take a point Q here, so that's the fiber of Q. And here is somewhere the image of this point. M is equal to alpha of Q. So we can think of alpha as a differential form on M, but we can also think of it geometrically as a map from the base to the total space of the cotangent bundle. And of course, of course, here there is this condition verified if you first apply alpha and then apply pi, so then you'll get an identity of Q. So you have two interpretations of alpha. One interpretation as a differential form and another interpretation as a map. And if you don't mind, perhaps I will be using the same letter, but we'll be using these two different meanings of alpha. So now a proposition. So there is a unique one form on T star Q such that alpha star theta is equal to alpha for all one forms on Q. So you see that's a very strange equation. That's because on the two sides we are using alpha in a different meaning. Right? On the right hand side alpha is a one form on Q. But on the left hand side alpha is a map. Right? And we take a pullback of theta with respect to that map from the total space back to the base. Right? Okay. So let's try to prove it. In fact, this will be a direct proof, and I'll simply give a formula for this theta and then prove that it works. And then we'll discuss uniqueness. So let's say we choose a point M in T star Q. Its projection is the point Q. And so we choose V in the tangent space at M of T star Q. And I need to tell you what will be the pairing between my one form and this vector. Right? And I define it by the following formula. Right. So the formula is very simple, but let me explain the notation. First of all, here maybe we should agree about this pi lower star. So for me, pi lower star. So that's the tangent to the projection map, and it goes from the tangent space at M to the total space to the tangent space at Q, which is pi of M of Q. Sometimes probably, another notation for it is probably d pi M. I don't quite know which notation you prefer. So that's the map which pushes forward vector fields. Whatever you like. Which one would be whatever. Right. Okay. Now very good. So this is an element of TQQ. And note that this is an element of T star Q, right? Because this is just a point of the cotangent bundle. So therefore, the pairing between them is well defined. Right. So the claim is that this theta verifies the conditions. All right, so let's try to check it. So I take alpha star theta. And I would like to, so this is now a one form on the base. And it lives, so this lives in T star Q of Q. So I should pay it with a vector from the tangent space. So this is equal to what? This is equal to theta, and here the push forward for vector fields, right? I can take alpha from one side to the other side. And now I should compute it. So I should compute it at the point M. So what is the point M? So the point M, so pi of M is equal to Q, but M is equal to alpha of Q, right, in this story. So my point M is equal to Q, and this is alpha of Q. Sorry. Right. Okay. Right. So now let me No. Sorry. I think I went too fast. Right. So. Right. Now I should write it M, and here pi star alpha star of U. Right. But now this, so this map is actually identity, right? Because if you go up with alpha and you go down with pi, you get the identity map. So the tangent of the identity map is the identity map. So this is simply identity. So this is equal to M U. And well, recall that M is equal to alpha of Q. But that's actually, see, that's actually what we wanted to prove. We wanted to prove that alpha star theta is equal to alpha. And that's what we proved. So all right, so the form theta satisfies the conditions that we set. Now, why is it unique? So here maybe let me do a little bit of hand waving. So theta is unique. Why is that? So let me use this defining formula, right? So I know that alpha star theta U is equal to alpha U and is equal to theta alpha star u, right? So u was in some tq q, and so this is a vector in t of t star q at the point alpha of q. So that was our axiom, right? So our axiom defines for us theta on all the vectors which are of this form, right? Because the right-hand side is well defined. So whenever you get a vector of this form, theta is defined there. So let's imagine geometrically what are these vectors. What kind of vectors you can get as images of all possible alpha star maps, because alpha you choose as you want, right? It's any smooth one form. So let me try to make a picture. So suppose this is a point M and T star Q. So that's right. So that's the corresponding tangent space. Well, maybe my picture is not very convincing. So this is the tangent space of M of T star Q. And inside you have a vertical fiber, right? So these are vertical. Vertical vectors. Now, what kind of vectors can you obtain by this operation? What do you think? What kind of vectors can you get there? So right, you take a vector on the base. So u was a vector on the base. Now you have a map from the base to the cotangent bundle, and you are mapping your vector there. What kind of vectors are you going to get? Let me ask you a test question. Something like this. Can you get? Do you understand my question? So, okay, let's look at it again. So, right. So you have a base of our vector bundle, right? So here is the total space. Let's make it very easy. Imagine that Q is just a real line, okay? Now, that's the cotangent bundle of the real line. Here is sitting the zero section, so that's this R again. So we choose a point Q here. So that's the fiber of Q. Now we're choosing a point here. It's called M. The tangent space at this point, you can imagine it, roughly speaking, is just, right? There is this tangent plane sitting at this point, and you can think that it's just lying on the cotangent bundle, right? So these are, so things here are tangent vectors. Now, what are those alphas? So an alpha is a map from R to the cotangent, to the total space. So an example of an image of alpha is something like this. Right? So alpha maps the base into the total space such that alpha composed this projection returns you back on at the point where you started. So in the picture here, suppose that I've chosen a tangent vector here, right? Here there is also a tangent space. It's just one-dimensional. So what will be the images under alpha star of the tangent vectors here, up there? How do they look like? So that returns to like first-year calculus. What are they, those tangent vectors? So I take an image of this guy here under the tangent map to alpha. What do I get? Right, I get a tangent line to this graph. Right. So now, suppose I am free in choosing my tangent vector and the section. So what kind of vectors do I get in total? So here I got a line, right? If I choose another alpha, I will get another line.
So you get everything but the vertical?
That's right. So I will get, that's what I was about to say, but that's good, exactly. So I'll get everything but I cannot, right? I can never get this vector. So that's true. But all the other vectors I can get with this construction. And not only for the real line, but in general case. Can we agree on that? So this means that actually, so these vectors, these are all the vectors but the vertical vectors. But this means that since theta is a smooth linear form, right? If you define it on an open dense subset, then like it's defined everywhere. So this, a dense. So these vectors, they span a dense subset. When you vary when one varies u and alpha. Of course, if I only vary u, then typically you see here I would only get a line. But when I start varying alpha, I can get many lines, and I will span a dense subset of this tangent space. So, and this means that theta, which verifies this equation, is unique because it's defined on a dense subset. So theta is unique. Right. Let me demystify. Of course, probably many of you, or maybe all of you, already know this theta. So I now introduced it in a somewhat mysterious fashion, but let me demystify it and compute in a local coordinate chart. So let's choose a coordinate chart on Q. With coordinates Q1, Qn. So then we can introduce the corresponding coordinate chart on T star Q. So if we have a point here, right, it's what? It's a cotangent vector, right? It's a cotangent vector to Q. And a cotangent vector, what is it? We can write it as a sum of coefficients that we denote by P times the canonical differentials of the coordinates Q. And so the coordinates now will be Q1, Qn on the base, and P1, Pn in the fiber. So these are coordinates. Coordinates on T star Q, and then the claim is that our form theta, recall that theta is defined canonically, right? But in this coordinate chart, it will have a form pi dqi. So why is it true? Well, we need to verify this, this property, alpha star theta is equal to alpha. Well, let's take alpha in one form on Q, and let's compute alpha star theta. Well, maybe I should still kind of recall. So here, the coordinates Q, they live on the base. The coordinates P, they live on the fiber. So in particular, like the first question, what happens with dQi's when you take a pullback by alpha? Nothing, right? So, I mean, before we define them as coordinates on the total space and as coordinates on the base. So maybe it's a little bit misleading that we call them by the same letter. But so of course, when we pull them back, so they just become coordinates on the base as they always were. Now, what happens with PI's? Just to be more suggestive, let me say that our one form in this coordinate chart, it can be written as a linear combination of dQi's with some coefficients which depend on Q's. So what are the pullbacks of PI's? PI is a function on the fiber. It tells you where you are sitting on the fiber. And where are you sitting on the fiber if you are using the section alpha? So what are the coordinates? You see that's the map alpha maps you here, right? What are the coordinates in the fiber of that point? How are they called? They are called alpha I of Q, right? So that's just their name. That's where this map maps you. So as a map, alpha maps you from the point Q1, Qn to the point Q1, Qn, alpha 1 of Q, alpha n of Q. Right? That's just, you see, that's the dual nature of alpha. When you say it's this one form, if you convert it into a map, that's this map. So this means that these are alpha i's of Q. And of course, this is simply equal to alpha. So this, our old friend of ours, right, this form pi dqi, it just has this property, it turns out. And that's very nice because this means that on the one hand, we have this universal property. It's defined universally independently of any coordinate choices. But on the other hand, once we do make a coordinate choice, it really looks very easy. Now, a simple proposition T star Q with omega. Let me still call it omega 0, even though we already had one omega 0. Let me also call it omega 0 equal to minus d theta is symplectic. And the proof is now one line. So we need to check two conditions. The first condition is that d omega is 0. This is obvious because omega was defined as d of something. So this is minus but now there is this other condition. That omega is non-degenerate. And here the proof is as follows. Choose a coordinate chart on Q such that the point of your choice belongs to the pre-image chart, let's say U. Pre-image of this chart on the canonical projection. So that's the place where you want to study your form. So then you know that theta is of this form. Theta is of this form, right? So then omega naught in the corresponding coordinate system is minus d theta, and this is minus d sum from 1 to n pi dqi, and this is equal to sum from 1 to n dqi wedge dpi. And this guy is non-degenerate, right? So about this guy, we don't have any doubts. And non-degeneracy is a local statement, right? You need to check it at every point. Now, you can check it at every point because around any point you can choose such a coordinate chart, and there you know what your theta is, right? Now you don't have any equation with gluing or anything. So theta is canonically defined, therefore omega is canonically defined, and when it suits you, you kind of look at it as a global problem and you calculate. When it suits you, you look at it as a local problem and you calculate. So all in all, so with those cotangent bundles, we get another huge set of examples. My lecture didn't quite fit into what I planned, and because of that, there is some small logistics problems, but I think that we will have to live with it probably. So in the exercises for the next week, I think we have one exercise where about the Keller manifolds, which is not covered, but probably many of you anyways know what Keller manifolds are, and well, just if not, then next week we start with it, and then well, for the exercise, kind of you will have to solve the exercise just after the lecture. Okay, well, let's stop here and let's have a break before the exercises.